Hi, today we will present our A2 assignment. I'm Ko Ziji and these are my teammates. I will start the first questions. Differentiation is widely used in solving mathematics-related issues, such as engineering problem. It is a process of finding the rate of change of a function at any given point. In this case, differentiation is used to determine the location where a bridge experiences the maximum bending moments. As shown in the figures provided, a bridge in Kolkata collapsed, and this may be due to the being improperly designed and built by the relevant authorities. The structure of the bridge didn't have enough strength to withstand the heavy loads acting on it. Eventually, it collapsed, leading to over 20 people injured and 3 deaths. To prevent this from happening, engineers should carry out differentiation to obtain the maximum bending moment the bridge will experience and exactly where it will happen. Now, I'll pass it to Qiyuan.
Now, let us move to a specific calculation. A simply supported bridge beam has a length of 50 meters and is designed to withstand maximum uniform distributed load of 20 kN per meter. In this question, we need to determine the location that the bridge experiences maximum bending moment and calculate the magnitude of that moment. Before go into the differentiation, we set the length of the bridge as L and the maximum uniform distributed load as W. The formula of the bending moment of a simply supported beam with a uniform load is mx equals to W times x over 2 times bracket L minus x, where x is the distance from the left of the bridge. By substituting the values given into the formula, it will give us the equation mx equals to 500x minus 10x squared. Next, we differentiate this equation with respect to s. The derivative dm over dx equals 500 minus 20x. It is important to note that this derivative represents the shear force, which is the internal force resisting the sliding of parts within the structure. The maximum bending moment occurs where this shear force is 0. Hence, by substituting the dm over dx into 0 and rearrange the equation, we can get 500 equals to 20x, making x equals to 25 meters after the division. To verify whether this is a relative maximum or minimum, we will carry out the second derivative test. Differentiating again gives us the value of negative 20. Since the second derivative is less than 0, the critical point is confirmed to be a relative maximum. Now, we calculate the magnitude by plugging x equals to 25 meters back into our original formula, and enable us to find the magnitude of the bending moment, which is 6,250 kilonewton meter. Now, can Yuan help me to conclude up this part?
Okay, thank you, Qiyuan. So as a conclusion, it shows that the maximum bending moment will happen 25 meters from the side of the bridge, and the magnitude is 6,250 kilonewton meter. Therefore, engineers must decide carefully on the materials and structure, ensuring all of them can withstand more than this bending moment before building the bridge to avoid collapse. Next, let's move forward to the second question. The second question using integration to determine the total force exerted by the water on the dam's face. If a dam is not properly designed, it may not be able to withstand the pressure of the water pushing against it. For example, we show a video of a dam collapse. So as shown in the video, when the dam structure is too weak, the increasing water pressure can cause it to completely collapse. In order to avoid this situation, the engineer must calculate how the pressure of water change with depth using integration. This example demonstrated below, and I will pass to Yu Yang to continue.
Thank you, Yuan Ling. From question 2, the problem states that a dam has submerged a face that is rectangular plate 50 meters wide and 20 meters high. The water level is at the top of the plate. What is the total force exerted by the water on the dam's face? First, let's understand why we can't just use the formula force equals to pressure times area. This is because the water pressure is not constant. It increases with the depth, meaning that the force is not uniform. Therefore, we need a method to sum up the tiny forces acting at every single dam. And that's where integration comes in. First, let us define the variables. Besides the height and width given by the problem, we need to know that the density of the water is 1,000 kg per meter cube, and the gravitational acceleration is 9.81 meters per second square. The pressure caused by a liquid at a certain depth is given by the formula P equals to rho GH. Substituting the values in for the water's density and gravity, we get the pressure at a depth H equals to 9,810 H. Now I'll pass it to Yanling.
Thank you, Yueyang. To continue, you need to divide the dam face into tiny parts where the pressure can be considered constant. We assume a thin horizontal strip at depth H with a thickness dH. The area dA is its width times its thickness 50 dH. The tiny force dF on this strip is given by dF equals pH dA, which simplifies to dF equals 490,500 HDH. The total force exerted on the entire dam is the sum of all these tiny forces, dF, from the top of the dam to the bottom. We integrate dF from H equals 0 to H equals 20. After a series of calculations, we can get F equals 9.81 times 10 to the power of 7 newtons. This data is important for engineers to decide material use and structure for dam walls. Hence, they must design and construct dam walls that can withstand more than this calculated force. In conclusion, integration helps engineers to calculate total water pressure and ensures the dam is safe, stable, and capable of protecting the surrounding area from possible collapse. That's all from us. Thank you. These links are our reference links.